welcome everybody. Thank you very much for coming. It's our great pleasure to have Hermann Karcher from the University of Bonn speaking today, and he'll talk on numerical experiments with closed constant curvature space curves. Professor Karcher, please go ahead.
I want to say a few words how this started. In most of my differential geometry papers, estimates occur, and those estimates come about by integrating curvature information along curves. And therefore, in all my differential geometry lectures, I have treated curves, but with some dissatisfaction, because there's a huge number of famous planar curves, but very few famous space curves. And in particular, with my preoccupation with curvature, I had liked to have constant curvature space curves in my courses, but I could only find examples which were pieced together from pieces of circles and helices, and those I didn't wish to treat. And this changed in 2007. And the project then was to write code for our program such that ODE-defined curves would behave as if they were explicitly parameterized. And then let's see what is the ODE in question. It's called the Serre-Frenet equation. It's known since 1850. And you will also be surprised a little later why up to 2007, there were no smooth constant curvature space curves, because many of them are actually rather easy to get. And you'll see that. Now, I don't know how much I should explain. T is the tangent vector, the unit tangent vector. Then n is the unit vector in the direction of the derivative of this thing, and b is the cross product of the two. And because of these sign changes here, this 9-dimensional linear system has the property, if you start with an orthonormal basis, then at all times the vectors t, n, and b are orthonormal. And therefore, if you integrate the first one, you get a curve which has this curvature and this torsion. And I didn't write kappa of S here because we will only be concerned with constant curvature curves today. And then as soon as you try to write code, you have to find simple functions for the torsion, which you can control by a few parameters. And we were using this one. And then it is pretty quickly clear that if the torsion function has zeros and is skew symmetric with respect to its zeros, so satisfies this property. Can one see this highlighting? Yeah, okay. Then the normal plane of the curve is the symmetry plane of the curve. And then if you have two of those, then reflection of the first plane in the second will produce a third one, and so on. And if the first two intersect with a rational angle, then automatically these curves will close. And therefore, any one parameter family of these curves will have closed curves. I have to pause because of this zoom menu. Now it's going, that's again. So I have to do that. So you should have the glasses on for this. So I do this again. And yeah. So maybe before I run this again, the curve has these symmetry planes, and about the dotted lines, I talk a little bit later. And now I run this again, and you see the angle between the symmetry planes is changing, and then every so often you hit a rational angle, and then the curve is closed. So for example, this one is practically closed. No, I missed it. This one is, this is the one we had at the beginning. Now, the problem is that most of the curves which I get this way have self-intersections. And of course, one really would like to have them embedded. And then among the embedded ones, there are only a rather few. So you see this sort of tennis ball shaped curve, and then you can have more symmetry, so higher dimension. So instead of having 90-degree angles between these symmetry planes, you can have 60 degrees and so on. But essentially, they just go up and down. And before I come to more complicated ones, I would like to say a few words about what you can see, and what you cannot see in the pictures which I'm showing. So this is a helix. This is the best known non-planar space curve of constant curvature. And I will run the osculating circles along this thing. And so these circles have at the point of contact, the same curvature as the curve. This will be the case always. And I'm using these circles to show you the curvature. So these circles are my way of visualizing the curvature. And there's unfortunately one drawback. If you do that for plane curves, you can see in the picture whether I'm cheating or not. But for curves in 3 space, I do not know what feature you have to look at to be absolutely sure that I'm not cheating, but these circles are computed correctly. Now,
Hermann, a quick question. The yellow, or well, I don't know what color it is for you, but the curve at the center of those oscillating circles
is the evolute. It was traced by the center of these circles. So it's called the evolute. And one of the properties of constant curvature curves is that the evolutes have the same curvature as the original curve. Now, this looks kind of strange to you because obviously the original helix is pretty curved, while the thing in the middle looks fairly straight. And therefore, I will change the parameters. And so the first two, I changed the radius of this thing. So now you see almost the same thing, but it is not the same because if I run the osculating circles, then they are now approximating the central line, and the midpoints of the circles draw the original helix. So this one has to learn that curvature of space curves is not so easy to see from a picture because I can't help. For me, the middle line is more straight than the outer helix. And my feeling is that that must be true for practically everybody. Okay, now I can come back to these constant curvature space curves. And we have one more symmetry observation. So if the curve, the torsion function is symmetric with respect to some parameter value, then the principal normal, so the line in the direction of this vector n in the differential equation, is a symmetry normal, which means 180-degree rotation around that normal maps the curve to itself. And that means if the two neighboring symmetry normals intersect with a rational angle, then automatically you get a closed curve. So that means we have reduced the problem to solving 2 parameter problems to get closed curves. And I come back and show you some. I will rotate this thing. And from some directions, you cannot see it very well, but you will see that the symmetry lines are in a plane and meet under 120-degree angles. And you also see that 180-degree rotation around these things map the curve to itself. So the next thing I want to show is why I can easily get many closed curves of constant curvature. So you should watch this plane, and what I will change now is the parameter which is the zero coefficient in the torsion function. So I should show you again. The torsion is this. So this is the average value of the torsion, and this is the factor of the sine part, and this is the factor of the 3s part. And I'm only changing this parameter now. Did I change it? No, I haven't. So and what you should see is that the distance between the symmetry lines increases very regularly. Now, that the different symmetry lines at each moment are equally spaced, that is part of the construction, because the third symmetry line is obtained by rotating around the second one, the first, and so on. So the important thing is that the distance between the symmetry lines depends in an extremely regular way on the average value, on the zero, on the constant coefficient in the Fourier polynomial of the torsion. And unfortunately, I cannot prove that. And the way I'm using this, I will show you next. I will change a different parameter. So I think, sorry. This is the coefficient of the sine term. And I will now use the fact which I just showed you to keep the symmetry lines coplanar. And then what happens is this. They keep staying in a plane, but the angle changes, and I simply wait until I hit a nice angle, and I'm heading for this one, and I hope I did the change large enough.
I mean,
yeah.
This is somehow some sort of amplitude that you are dealing with for the.
It's the average value of the torsion.
Yeah, that's the first one.
That's the first one. And,
yes. And now you're changing the second, is that right?
I'm changing the factor in front of the sine function, and I'm following. So here I didn't choose the number large enough, unfortunately. Mm-hmm. So I change this parameter arbitrarily, and it will be changed from this value to this value in 120 steps.
I understand.
And this parameter will change in such a way that the symmetry lines remain coplanar. So now I will reach the other one. So you can see in a very stable way. So now the program is written in such a way that at this moment, the curve which you see is the actual curve. And you can also see it's not quite the one which I'm after. So that can be done by changing this parameter by much less. So I think it will be enough to change this 2 to 9. And now they will move much more slowly. Now it's almost closed, but only to pixel accuracy. And I do this again. And then I have this program which adjusts two parameters simultaneously, and that is closing the curve to 10-digit precision. And you can see that the thick lines which you saw here have now the same thickness as everywhere. So this is now a 5-2 knot, which was obtained by this deformation from the original one.
This seems to be some sort of optimization process that is going on here.
No,
Getting it close, choosing these parameters. Would it be possible to
no,
auto?
I show you again.
Mhm. I mean, you are changing the parameters to get it closed.
So I need the symmetry lines, because without the symmetry lines, I can't judge what I'm doing. What I hope I got across is that the distance between the symmetry lines depends in a very regular way on this parameter, on this first parameter. So I'm using that parameter to keep the symmetry lines closed at each step of the deformation. And I arbitrarily change the other parameter. So we have gone in one direction. So now I go to the other direction. I think 56 is good enough. And now the same thing will happen. The symmetry lines will be kept closed by the automatic adjustment of this important parameter. And the angles will change because I change the other parameter, and I stop the program when I have reached a curve which I want. Now, what is happening is that the parameter in front of the sine function is changed from this value to this value in 120 steps.
I guess.
And that I have by changing this parameter and then say animate, this is what the program does. Now, simultaneously, the other parameter, it was much larger earlier, this parameter is changed so that the symmetry lines remain coplanar. And then as a result of that, the angle between the symmetry lines changes through the steps, and I stop the program when I have reached, for example, in this case, you don't see that yet. I have to make the curves a little bit longer. So now they are closed, and you can almost see that I made a 7-2 knot from the other one, except that the lines here do not quite close. So I do the same thing again. And now I think I did not quite reach it. So here I can make a mistake by going in the wrong direction. I decrease this number rather than increase it. And I hope that's the right direction. And then I keep changing and I watch these. And the moment, I don't know, maybe that was good enough. I try the two parameter problem. And if I call this program, it adjusts both parameters alternatingly. So, okay, you could see that it caught it. And so now we have a 7-2 knot obtained from the other one by this procedure. And it all depends on the fact that the distance of the symmetry plane lines depends in such a regular way on this constant coefficient in the Fourier polynomial for the torsion. And I have tried and tried, but I cannot prove that fact. And I'm very sad about that because I think that is the basis of everything. Now, in this way, I can make plenty of different curves. They not always look as simple as this one. So, for example, this one, I can add the symmetry lines to have a little bit of help. But I think you will agree it is not so easy to see what kind of curve this is. It's still a curve of constant curvature. Maybe we should briefly check by running the osculating circles. And the important thing is that the radius of this circle doesn't change. And that, if you believe that I'm not cheating, that proves that the curve has constant curvature. But obviously, since I wrote the program for myself, I compute the curvature correctly and not for some demonstration. Okay, now the same thing will happen here as which happened in the other case. I can again change this parameter arbitrarily. And then adjust to keep the symmetry lines closed. So you see, the angle between the symmetry lines changes, and I just have to wait till I'm close to something which looks promising. And then I click, and maybe this is okay, we'll see. That is maybe a little bit too complicated, and I try again. For me, it is slightly simpler to watch these lines in monocular. So I turn this off, and you can rest your eyes for a moment. And again, I rotate these symmetry lines.
I mean, in this picture, it seems to me that there are sort of three parts of the curve that are quite similar. Is that
Sure.
because of that three? Is that because of that three in that formula you have?
No.
Sine
no,
of three?
No. The three parts which are similar depend on the 60-degree angle. And I'm changing this angle. So now these parameters are set to the parameters of this curve. And I have to change one of them, and I decrease it. And now I have to watch the symmetry lines and stop at the right moment. And I have practiced for the simpler curves, and I haven't actually done it on this one. So I think I reached a higher symmetry, so I make the curve longer. Okay, 1, 2, 3, 4, 5, 6, 7. So now I happen to stop at an 8-fold symmetry of the same thing, or rather similar thing. So the vertical from the side, the different pieces look similar, but I have many more. So in this way, I can really get a lot of curves, but what I cannot easily get is when we now look at the osculating circles, then it follows this helix for a while, but then it returns, and we have all these cusps. So the evolutes are curves with singularities, and that comes because the torsion is zero, has zeros. And I have to find examples where the torsion never gets zero, and it took me quite a while to find one. But once I have one, this deformation process would work again, and I can easily make other ones. Now, this one was special because it suggested to me maybe you can find such examples on tori. And indeed, that is possible. And we look at the differential equations first. So a curve on a surface has a normal curvature, which depends only on the direction of the curve. So that is written here. And then a geodesic curvature, that is how it turns in the tangent plane. And then the space curvature squared is the sum of the squared of those. So therefore we get, and we can compute a geodesic curvature if we want to achieve space curvature kappa in this way from the normal curvature, which depends on the derivative. And that gives a second order differential equation. The second derivative of the curve is the normal curvature times the normal plus the geodesic curvature times this cross product, which is the normal in the tangential direction. And this differential equation gives curves of constant space curvature on a torus. And because of this, if kappa is larger than the maximum of the normal curvatures which occur, then this differential equation is a Lipschitz differential equation, and I can easily solve it. But if I want to have curves with smaller kappa, then I have more trouble, and we'll see what happens. So this computation, for example, is much slower than on the 10 years older operating system. And here, I think, so this curve is obtained. I start at the equator, at an equator point, tangential to the meridian of the torus, but I prescribe a space curvature which is larger than all the normal curvatures of the torus. And then this thing turns around until it hits a meridian orthogonally. And then by reflection, I get automatically a closed curve. And then I can also start this at the inner meridian by just changing a sign here. And then this is also a space curve of constant curvature, which we better check by running an osculating circle around it. So when I do this on the old system, the circle just races along, and I have to show you this slow performance, but you see the radius of the circle doesn't change. And we get these easy constant curvature space curves on every surface of revolution. And so, for example, I can show you on an ellipsoid. Come on. And on a cylinder. So this I can find quite fascinating. Several years after my teaching stopped, I found that on a cylinder, which is really one of the simplest surfaces you could think of, you can find constant curvature space curves like this one. And then there are even more. We are back at the torus, and I want to change the symmetry. And now this curve starts at the equator, and I choose precisely the norm of the space curvature such that the geodesic curvature at this point on the equator is 0. And then the geodesic curvature becomes larger in absolute value on both sides of the equator, and I choose one sign below the equator and then the other sign on the other side of the equator. And in this way, I get these oscillating curves oscillating up and down from the equator. And they also exist on these other curves, on the other surfaces, sorry. And you see, this is an ellipsoid of revolution, and we have a similar up and down oscillating curve around the equator. And finally, on the cylinder, we also have this. And then I decided to look at the differential equation on the cylinder, because the cylinder can be rolled, a plane can be rolled onto the cylinder in this way. This is an isometric wrapping of a plane with coordinates x, y onto a cylinder of radius r. And in the plane, a curve can be obtained from its geodesic curvature by first integrating the geodesic curvature and then writing down the tangent vector of the expected curve in this way, and finally integrate the derivative to get the space curvature. And then what we started with, we have a first order differential equation for this turning angle. And again, it is Lipschitz if kappa is large enough, and it is not Lipschitz if kappa gets too small. But then something similar as with the sine function happens. The first order differential equation for the sine function is sine prime equals square root of 1 minus sine squared. And that is not Lipschitz when the sine is 1. And in fact, you get you get other solutions, namely that first order equation has the constant solution equal to 1. And similar, that is the same here. We also get constant solutions of this first order equations, which are meridians, and we don't want to see those. But if you differentiate the first order equation for the sine function, you get a linear Lipschitz equation, which everybody uses for the sine function. And similarly, in this case, if you differentiate this differential equation, you get this second order Lipschitz equation. And therefore, we can compute much better than with the equation I used on the torus. And we find something surprising. So first of all, I can now wrap this thing. I'm fighting Zoom at the moment. So what do I have to do? Mute all. No, how do I get rid of this? Here, maybe, yeah? Yeah, okay. So this is a circle, and we roll the plane, and we keep this curve, a space curve of constant curvature. So it will get a somewhat elliptical shape, but of course it's not an ellipse, but it has constant space curvature, and we can follow this. And yeah, I hate how slow this is, and I stop it. I just run. Come on.
Sorry, can I ask a two-dimensional question?
Yeah.
Do you know anything about the surface which is enclosed by this curve? So the torus surface that we saw earlier, or here the cylinder surface, is it some sort of
I have
mean
not
curvature
understood.
surface?
Let me show this a little bit further. So now the meridians have this radius or this curvature, and I change this to get closer to this. So I put 0, 0, 1. And then the curve wraps around the cylinder somewhat more, and it stays closer to the meridian at this point for a while. And I can throw in more zeros. Could it be that the computer is further slowed down by Zoom? Because
yes, that could
course,
be.
I practiced, and it is slower than I thought it should be. So you can see the more that this thing is going to wrap around more and more. And finally, if I use precisely the correct curvature, then I get a curve on the cylinder, which is asymptotic to a meridian. So here it is asymptotic to the meridian. And then in the other direction, it repeats, it has a reflection symmetry here. But since I have to start in this tangential direction, it would have made too much extra programming effort to get it in the other direction. And I also show you what happens when I go below the curvature. So it's 6, and then
just a question. So you get a complete curve, but it's not proper. Is that what happens in that case?
So I always start here, and now we have a curve which is, this is how long I computed it. And now I get closer to 0 by adding more 9s.
When you now have a surface of revolution, is there some sort of Clairaut theory here, maybe?
These are not geodesics.
No, I know, but a Clairaut theory for surfaces of this type, no, for curves of this type.
I don't know.
No.
I don't know. Okay, so in this way, we get, even on a cylinder, on the simplest surface you could think of, we get plenty of constant curvature space curves, which were not known while I was teaching. And I'm really sad about that. I would have liked to show this. Now, at this point, Eckhart Jarden gets into the game, and he asked, can you find space curves such that the evolute is congruent to the original curve? And for that, he changed the differential equation slightly. First he has to compute that the evolute has the same curvature as the original curve. I said that already. And that the torsion of the evolute can be computed from the torsion of the original curve quite easily. And then he changed the Frenet equations to an equation where you parameterize the curve no longer with constant velocity, but with given velocity v of t. And then it is done with such a function which changes after, by adding pi, you go to 1 over this thing. And the result of this differential equation is, for every curve which solves this equation, the piece from 0 to pi on this curve is congruent to the evolute from pi to 2 pi. So I'm going now to show you such curves, and then I'm afraid I have, oops, sorry, this is a constant torsion. I slipped. I think we look at this as a tube. So here the torsion is large. Here the torsion is small. Here the torsion is large. Here the torsion is small. So these are two pieces of the type I described. So this is parameterized from 0 to 4 pi. And it closes up because the curve again has symmetries. And I made the symmetry lines meet under 90-degree angles, and therefore rotation in these symmetry lines closes the original piece to what you see. And I show some more examples, and then I'm afraid I have to quit. So this has also 90 degrees symmetry lines, but it stays, the torsion is so small that it wraps around this thing twice, and then you can also change the symmetries of this thing. So this is kind of a dull curve, but it is congruent to its evolute, which I'm not showing. And another example, so what you saw with the other one, it has very small torsion for a while, and eventually we get to a knot. And here we take off your glasses for a moment. I show you this as tube. And so you see clearly the torsion is very large here, and the torsion is small here. And when we go back to the curve, we watch the oscillating circles. Again, they are annoyingly slow, but that's not, I can't avoid this. So the circle is oscillating here, and the midpoint of the circle traces out the same curve, just half of the length of the curve apart. And these curves, Eckhart and I call autoevolutes. And Rob, I think you have, where is this thing here? You have looked at knots made from ropes of a finite radius. And these curves have the property that you can make a tube around them so that it touches itself along the middle line between the curve and the evolute. And these pictures must be somehow connected to work which you have done in some distant past. Okay, and I want to show maybe what is this? Two more examples, and then I have to quit. So this is a knot, a 5-2 knot. And so this one, maybe we should also look as a tube. I don't know how much the stereo helps here, so I switched to monocular. And now you see from the coloring that here the curve twists really a lot, and the normal of that curve wanders around this loop while the oscillating circle touches here, and the other way around, while the oscillating circle touches this loop, this rotating thing, the radius traces out this part of the curve. Okay, So I think I stretched the time. I need to close, and I thank you for your attention. And I hope that you at least enjoyed some of the pictures, and certainly I enjoyed finding them. Thank you very much.